Hello everyone, I am Mahdi Rahimi and today I'm gonna present LARMix++, Latency-Aware routing in mixed network with free routes topology. So to make sure we are on the same page, first I'm gonna introduce briefly the anonymous communication systems, and then we will see as a result of using these systems, actually the quality of service may affect it. Then we will try to see how we can address that using LARMix++, which shows that we can use it to enhance actually the quality of service without losing much on anonymity. Okay. To start, as you might know, when two endpoints on network want to communicate, by default, their communication will be secured using cryptographic protocol, right? However, the fact that these 2 points are communicating is not hidden from the perspective of a network adversary who is observing this. And it can be problematic. It can actually raise some privacy issue that we need to address. To address this, one of the typical choice for a client is to use the Tor network, which is an overlay network, consists of some relays, and a client who wishes to have an anonymous communication to destination can pick some relays from this network that we usually call them guard, middle, and exit relays. And then she will start encrypting her packets with the public key of the exit, middle, and guard relay respectively. And in this scenario, after receiving each packet by nodes, they're gonna pull off one layer of encryption, and then they know to whom they should submit or forward these packets. In this case, as long as these nodes are not collaborating, so we can say that client has some sort of anonymity. However, with the assumption that the internet service provider that owns the network between client and guard relay is not the same as the one who owns the network between the exit and the destination. So, as you might guess, if we imagine a scenario that actually these two internet service providers are the same, then we have a problem. Because this internet service provider can collect the data of packets the client sending to the Tor relays, and also he can observe the end of the Tor network and see all the packets and collect the timing and sequence of the packets and try to launch a correlation attack, which with high accuracy helps him to actually de-anonymize the client to the destination connection. So that shows that Tor is not that secure. What to do? In order to provide a stronger notion of anonymity, first we need to have a good understanding of mixed network. For that, first we need to understand how mixing works. So let's consider an entity in the network that receives traffic from different sources. And after receiving this traffic, it's gonna mix this traffic or shuffle them and wait for some moments and send the traffic out. In this case, an adversary who observes this scenario has no idea how to link the input to the output of this entity, that we call this entity as mixnet. It can actually help us to provide a stronger anonymity in network. Having this in mind, then we can consider a network of such nodes that we usually call it mixed network or mixnets. In this scenario, then a client again can pick out some mixed nodes from the network to make some message routes, where her messages not only will be forwarded to some intermediary nodes, but also will be shuffled and mixed with other packets. So in this scenario, if that internet service provider tries to corrupt all parts of the network, it still has no idea who communicates with whom, right? Even we can go crazy with that. We can consider that that internet service provider also wants to provide some mixing operation in mixed network, like here. In this case also, as long as just we have one mixed node that can honestly operate the mixing, we can assure that we have anonymized communication where client to the destination. Okay, that's great. We had the problem on internet concerning the privacy of users, and we can kind of solve it perfectly using mixed network. However, mixed network provides this high anonymity at the cost of high latency. The latency in mixednet is high because of two reasons. One of the reasons that might be obvious is that the client should forward their messages through some intermediary nodes. These intermediary nodes can be from different continents, and they might have like high distance from each other, right? High latency. So it will contribute to heighten the end-to-end latency. Not so good. Not to mention that the second reason is that each relay, in order to mix the traffic, will add some delay for shuffling purposes. That also contribute to heighten the latency. So that can be too bad. We have high anonymity, yes, that's true, but the client actually cannot adopt the mixednet in this scenario for, let's say, web browsing or instant messaging. That can be a very critical problem. We need to kind of find some ways to solve that. The first work that attempts to provide some solution to lower the high end-to-end latency in mixed network was LARMix that recently published. LARMix actually proposed that, okay, we can have some algorithm for assigning mixed nodes to the mixednet, and also some node selection and routing strategy that can effectively lower the end-to-end latency. And that's true. We can use that actually. However, they have an assumption. They did that on top of a mixed network that is formatted in a layer structure. So layer structure usually is useful. It has its own pros and cons, but it has some issues, specifically when clients do not wish to trust a central point, or they do not wish to spend extra cost on mixed nodes. In order to make sure that the mixed nodes are fairly assigned to the mixing layer. That is the extra operation that they need to do. In order to avoid that, there are some other topology of mixed nets that we do not consider any layer formats. Because actually, in layer structure, we need to fairly actually decide how to assign the mixed node to the mixing layer, right? We need to divide them somehow in layers. But we can also consider a case that we do not need to do this, and we will just consider a free root topology where each node can freely be connected to every other node in the mixed network. In this scenario, we don't need to have that extra cost. And actually, as you might guess, this is the topology of network that we consider for LARMix++, and we want to provide the low latency scenario for this topology as well, contrasting to the topology that has been considered by LARMix. Okay, after having this setup, then we can continue with the strategies we have in LARMix++. So in LARMix++, we propose some routing strategies for the client to help her, to prioritize the low latency links. First of all, we assume that the client has the information regarding the latency between the nodes in the mixed network. And then client will adopt the LARMix++ approaches to make sure that high latency links will be selected with low probability and low latency link will be selected with higher probability. And if we actually adopt this approach, that means that on average we will have lower latency than baseline case, that we will randomly select every other nodes with whatever link latency they have, right? So this was the first approach that we proposed in LARMix++. As a result of using this approach, then we found out that there might be some nodes in mixed-nets that will be selected more frequently compared to others. That means that they will receive higher traffic. It can be actually problematic because there might be some mixed nodes that they don't have enough capacity to handle the extra traffic. And they need to actually delay the packets in order to make sure they have enough capacity or enough room for them to be in, right? So it will unintentionally, again, contribute to higher end-to-end latency. To avoid such cases, we provided algorithms that help us to make sure that mixed node in the mixed network more or less receive the same amount of traffic. For an instance, you can consider this figure that green, red, and blue clients wants to most likely send their packets to the first, second, and third mixed-net respectively. In such case, our algorithm will make sure that still we kind of maintain their preferences, but every node, as you can see, will receive the same amount of messages to make sure that they will not be overwhelmed by just, perturbing our probability distribution in the network. Okay, that's great. So having these strategies in mind, then we are ready to evaluate the LARMix++ with two metrics that we usually consider. One of the metrics that we always consider is the average latency, because remember, we wanted to reduce this latency, so we need to kind of consider that, right? Apart from that, typically in mixed network, we consider another metric to make sure that we are not damaging anonymity that much. And actually, this metric is message anonymity, which actually consider a scenario that we have a global network adversary, as you might see, that this adversary targets some messages in the input of the mixed nets. And then he will look at the output and try to find the messages that are most likely correspond to the targeted messages. And in this case, he will drive a probability distribution, and the entropy of this distribution actually would be the metric that we're gonna consider. We want to make sure we're not gonna damage this metric that much using our approaches. Okay, so considering our strategic routing approaches, our balancing algorithms, and the metric we want to evaluate, then we can show some of the main results of the LARMix++. We actually perform many experiments. Here I'm just showing the main ones to you. So in one experiment, we considered that the client can just uniformly at random select the nodes in the mixed nets, and then we measure the latency. In this case, the latency was in the highest level, 125 milliseconds. But also the anonymity was quite high, like 12 bits of entropy. However, when we adopted the mixed nets with our strategic routing, we understood that we can reduce latency to 50 milliseconds, 60% of reduction, that looks really good, just at the cost of losing just half bit of the entropy. That can be not so critical. Apart from that, we also consider a scenario that client wishes to have low latency routing, but they don't want to overwhelm the mixed-net with the messages. In such case, we observed that we can reduce latency to 75 milliseconds, 40% of the reduction, while we will just lose 0.2 bits of anonymity. That can be really negligible. So compared to the uniform case, It provides everything, just losing a bit of anonymity. So that looks really great. And in conclusion, I want to just recap that we have a really concerning issue on internet regarding the identity of the communication endpoints. To provide anonymity for those points, we definitely can adopt Tor network, but is vulnerable to the adversaries observing both ends of the network. To make sure we have higher anonymity, we can definitely use mixed network. But mixed network will heighten the end-to-end latency, actually degrading user experience in the mixed net. And finally, to have acceptable latency, we can adopt approaches like LARMix++ that can reduce the latency by 60% compared to the baseline, not to mention that the anonymity also will be maintained to some good level using LARMix++. So yeah, that's it. End of my talk. Thank you so much for listening. If you wish to know more about this topic, don't forget to visit my webpage. And you can also share your ideas with me through my LinkedIn. Thanks.